Welcome to the deep dive.
Yeah.
Today, we're diving into something a little different. It's one of our very own AI CodeCast challenges. You know,
Okay.
those daily brain ticklers we throw at you
Yeah.
to keep those coding skills sharp.
Right?
Well, you sent one over that caught my
Yeah.
eye.
Oh, cool.
Something about grabbing letters from a string. And I've got just the person to help us unpack it.
Awesome.
Let's break it down.
Okay.
So imagine you have a string of letters, just A, B, and C.
All right.
Your challenge is to figure out the minimum number of steps it takes to grab at least K of each letter.
Okay.
Here's the catch.
All right.
You can only pick from either end of the string,
Uh-huh.
one character at a time.
Okay.
It's like you're choosing ingredients off a conveyor belt,
Mm-hmm.
but you have to get enough of each type.
Exactly. And that's where it gets interesting.
Right.
It's not enough to just find any way to get K of each letter. We're after the most efficient method,
Yeah.
the fewest steps possible.
Right.
It's like optimizing your grocery shopping route, but with code.
This problem has a sneaky complexity to it.
It does.
At first glance, you might think, let's just grab from whichever end has the most of what we need.
Right.
But that kind of greedy approach can lead you down the wrong path, right?
Absolutely. Let's say our string is A, B, C, C, and we need 2 of each letter.
Okay.
If we just keep grabbing C's from the right because there are more of them initially,
Uh-huh.
we end up having to backtrack later to get enough A's and B's.
Right.
That's not very efficient.
Not at all.
It highlights a crucial point. Sometimes the most obvious solution isn't the most optimal.
Right.
We need a way to think beyond the immediate and consider the overall picture.
So how do we even begin to tackle this? It feels like a bit of an alphabet soup.
Well, one way to start is with the most straightforward approach. Brute force.
Okay.
We could systematically try every possible combination of picking from the left or the right, keeping track of the steps for each.
So it's like exploring every single path down that conveyor belt of letters.
Exactly. We'd keep going until we find a combination that gets us at least K of each letter.
Okay.
Then we compare all the successful combinations and see which one took the fewest steps.
So with brute force, we're guaranteed to find the right answer.
Oh.
Eventually.
Yeah,
But something tells me there's got to be a more elegant way.
you're right. Brute force works,
Yeah.
but it can be computationally expensive.
Right.
Especially for longer strings.
Yeah.
The number of possible combinations explodes exponentially,
Oh, wow.
and it becomes really inefficient.
Yeah.
It's like using a sledgehammer to crack a walnut.
Yeah.
Effective, but there's got to be a more refined tool.
Right. So brute force is out.
Yeah.
What other tools do we have in our coding arsenal?
This is where a technique called the sliding window comes into play.
Okay.
It's a way to explore the string more efficiently.
A sliding window. Okay, now you've piqued my curiosity.
Right.
How does that apply to this letter grabbing challenge?
Imagine a window, like a little frame,
Uh-huh.
that you can slide along our string of letters. This window always needs to contain at least K of each of our letters, A, B, and C.
Right.
We can shrink or expand the window as we move it along,
Okay.
always ensuring it holds at least K of each.
So we're not just picking letters randomly.
Yep.
We're strategically moving this window to capture what we need.
Exactly. And the size of this window,
Okay.
the number of letters it covers,
Yeah,
is key.
Let me guess, does the size tell us how many letters we need to remove to get at least K of each?
You're close, but remember,
Okay.
our goal is the minimum number of steps to take,
Oh, okay.
not remove.
Okay.
The window size tells us the maximum number of characters we can remove while still having enough of each letter left over.
So it's like figuring out what we can get rid of
Yeah,
rather than what we need to collect.
precisely. We use this sliding window to find the largest section we can safely remove.
Okay.
Then we subtract that size from the total length of the string to get the minimum steps we need to take.
It's like figuring out the shortest route by calculating the biggest detour we can take.
Clever. So the sliding window lets us flip the problem on its head,
Yeah.
focusing on what we can discard rather than take.
And the best part is, the sliding window technique only requires one pass through the string to find the answer.
Exactly.
That's incredibly efficient compared to brute force, especially when dealing with those massive strings.
Oh, yeah.
This is making me think, though.
Yeah.
What if our string doesn't even have enough of one of the letters to begin with?
Okay.
Like, what if we're supposed to grab 5 B's, but there are only 3 in the entire string?
That's an excellent point.
Right.
We need to address those edge cases before we even start sliding our window around.
Yeah.
Before we do anything else.
Right.
We need a quick check to see if we have at least K of each letter in the string.
Gotcha.
If we're short on even one letter,
Yeah.
we know it's a no-go, and we can signal that by returning mate as 1.
It's like checking the fuel gauge before we start the engine.
Makes sense.
Yeah.
But what about another edge case?
Okay.
What if K is 0?
Uh-huh.
Does that mean we don't take any steps at all?
Yeah, exactly.
Absolutely. If K is 0,
Yeah.
our task is already done.
Right.
We have at least 0 of each letter.
Right.
Which is always true. It's a simple case.
Yeah.
But important to handle correctly in our code.
For sure.
These edge cases are where thoroughness really pays off.
Okay, so we've got brute force.
Yep.
Reliable, but potentially slow.
Uh-huh.
And our snazzy sliding window.
Yeah,
Efficient, but needs those pre-flight checks.
absolutely.
Where do we go from here?
Well, I think it's time to dive deeper into that sliding window approach.
Okay.
Let's break it down step by step and see how it really works in action.
All right, let's unpack this sliding window and get those algorithms humming.
Sounds good to me.
Let's do it. All right, so we've got this sliding window concept floating around.
Yeah.
Let's ground it by walking through how it actually works step by step. Imagine our string laid out like a track, and our window is a little car moving along it.
Okay.
Our window car is going to cruise along looking for the longest stretch it can bypass while still leaving enough A's, B's, and C's behind.
Exactly.
Yeah.
Our first pit stop is that pre-flight check we talked about.
Right.
We need to make sure we even have enough of each letter to satisfy that K requirement.
Yeah.
If we're short on even one letter, we know it's a no-go and return -1.
Safety first.
Yeah.
So assuming we have enough letters in the tank,
Right.
how do we get this sliding window show on the road?
We need a way to keep track of where our window is on this track.
Okay.
We use 2 pointers, which are like the front and back bumpers of our window car.
Okay.
We can call them left and right.
Gotcha.
At the start, both pointers are at the very beginning of the string.
Okay.
So our window is 0 length.
Okay, so our window car is parked at the starting line, ready to roll. What happens next?
Now we start moving the right pointer,
Okay.
expanding our window 1 character at a time as we go. And as we expand, we keep a tally of how many A's, B's, and C's are inside our window.
So it's like our window car is picking up letters as it drives along.
That's a great analogy. Now here comes the clever part.
Okay.
At every step, as we expand to the right,
Yeah.
we check if we can shrink the window from the left side.
Wait a minute.
Yeah.
Why are we shrinking the window if we're looking for the largest removable section?
Yeah.
Shouldn't we just keep expanding?
That's a great question.
Right.
It seems counterintuitive, but remember, we're looking for the smallest window that still leaves enough letters behind.
Okay.
Shrinking from the left ensures we don't miss any potential smaller windows that might work.
So it's like
Yeah.
we're trimming the fat as we go,
Yeah.
making the window as small as possible without breaking our K rule.
Exactly. As we move the right pointer,
Oh,
we're
cool.
constantly asking, can I nudge the left pointer forward without dropping below K of any letter outside?
Right.
If we can, we do it.
Yeah.
If not, we keep expanding to the right.
So it's a dance between expanding and shrinking.
Yeah.
Finding that perfect balance point for our window.
Exactly.
Well,
And every time we hit a valid window,
yeah.
meaning we have at least K of each letter outside, we check its size.
Yeah.
If it's the biggest valid window we've seen so far, we update our record.
So we're crowning a champion. The biggest valid window encountered during our journey across the string.
You got it.
Yeah.
Once our right pointer reaches the end of the string,
Right.
we know we've explored all possible windows.
The right pointer has reached the finish line. What happens then?
Our champion window, the biggest valid one, represents the largest chunk we can remove.
Okay.
To get the minimum steps to take, we subtract the champion window size from the string's total length.
We've driven the whole track,
Yeah.
found the longest detour,
Yeah,
and then figured out the shortest route by subtracting that detour from the total distance.
a perfect analogy. And that's the essence of the sliding window.
Awesome.
It's elegant, efficient,
Yeah.
and perfect for problems like this.
This makes me wonder,
Yeah.
are there any other situations where this technique comes in handy?
Oh, absolutely. The sliding window pattern pops up all over in coding challenges and real-world applications.
Like what?
Think about finding the longest substring without repeating characters,
Okay.
or calculating moving averages in data streams.
Wow. So it's not just a one-trick pony.
Yeah.
It's a versatile tool.
Exactly.
Cool.
Once you grasp the core concept,
Yeah.
you can adapt it to solve a whole range of problems.
Okay, I think we've got a good handle on the sliding window now.
Yeah.
What else should we consider for this AI CodeCast challenge?
Well, we've covered the logic,
Right.
but there's one more crucial piece to discuss. The code implementation.
You're right. Let's talk about how we translate this elegant sliding window concept into working code.
Yeah.
What are some key things to remember when we start writing?
One of the first decisions is how we'll store and update those letter counts as our window moves. Do we use arrays, dictionaries, or something else?
Right, because the right data structures can significantly impact our code speed.
Exactly. And then there's the challenge of turning that shrinking logic into code.
Right.
We need to ensure we're moving our left and right pointers correctly
Uh-huh.
and updating the counts accordingly.
It sounds like there are a lot of moving parts to juggle.
There are.
Maybe we should walk through a sample implementation to see how it all comes together.
I think that's a fantastic idea.
Right.
Let's choose a language,
Okay.
say Python,
Okay.
and write a clean and efficient version of this sliding window solution.
Perfect. That way, everyone listening can see how this works in practice.
Absolutely.
Okay, let's get our hands dirty with some code.
All right.
Python seems like a solid choice for this, nice and readable.
Excellent choice.
Yeah.
Python has some really convenient built-in tools for working with strings and counting things.
Perfect. So we're going to have a function, let's call it take characters. It'll take our string, S, and our target count, K, as input.
Exactly. And don't forget that initial check.
Right.
We need to ensure we have at least K of each letter in our string
Right.
before even thinking about sliding windows.
Right. Our fuel check before takeoff. How would we code that in Python?
Python's collections counter is ideal for this.
Okay.
It gives us a neat way to count how many times each letter shows up in our string.
Right.
We can then quickly see if any of those counts are less than K.
Okay.
If any are too low, we return -1 signaling. It's impossible to get what we need.
Gotcha.
Otherwise, we move on to the sliding window part.
Now for the sliding window itself, we'll need to keep track of the letter counts inside our window as it moves. Could we use another counter for that?
We could, but a regular dictionary might be a bit more efficient in this case.
Okay, so we have a dictionary to keep tabs on the letters inside the window. We also need those left and right pointers to mark the window's boundaries.
Right. We'll start both at 0, placing our window at the very beginning of the string. And of course, let's not forget a variable to store the size of the largest valid window we find, that we encounter.
Let's call that max window.
All right, variables are set up. Time to get this window moving and shrinking. How do we do that in code?
Yeah, how do we do that?
That's where a loop comes in.
Okay.
We'll use a while loop.
Okay.
It keeps going as long as our right pointer hasn't reached the end of the string.
Mm-hmm.
And inside the loop, we expand our window to the right, one character at a time.
Okay.
Updating our window's letter counts as we go.
Precisely. And with each expansion, we need to check if we can shrink the window from the left side without breaking our K rule.
Right. That's the part where we trim the fat to get the smallest possible window. How do we translate that into code?
Yeah.
We can use another while loop nested inside our main loop.
Okay.
This inner loop will keep shrinking the window from the left.
Uh-huh.
As long as we have at least K of each letter outside the window.
So the inner loop is like a tiny cleanup crew, making our window as compact as it can be.
Exactly.
Yeah.
And with every valid window we find,
Yeah.
we compare its size to our current max window.
Yeah.
If the current one is bigger, we update max window.
Got it. And once the main loop finishes, we've checked every possible window. Max window will hold the size of the biggest valid window we found.
Right. Finally, we calculate the minimum number of steps by subtracting max window from the string's total length.
It's amazing how all these pieces fit together into such an elegant solution.
It is, isn't it? And remember, this sliding window technique is surprisingly versatile. Once you understand it, you can apply it to all sorts of problems.
Absolutely. This has been a fantastic deep dive. I love how a seemingly simple problem can lead to such fascinating insights.
Me too.
And for those of you listening, here's a little something to think about. What if we had more than 3 letters in our string? Could we adapt this sliding window approach to handle that?
That's a great question to ponder. It's like taking the sliding window to the next level. I encourage everyone to explore that idea and see what they come up with. Until next time, keep those coding muscles flexed. And remember, the best way to master algorithms is to dive in and get your hands dirty.
Thanks for joining us on the deep dive. Keep those algorithms sharp.